Morning, weather and climate. We're nearing the end of the exam for material, and we're finally going to take a look at climate change. And this slide, it may become apparent why it's comical or not comical as we move along. The slide suggests that there is a debate. And some people think there is a debate about whether or not climate change is currently happening and humans are the cause of it. And in fact, in the scientific community, there is an overwhelming consensus among thousands of professional experts in the field that, in fact, the climate is warming and that humans are the cause. Now, that's not to blame humans and shame humans, that's just to speak a truth, and we're going to talk about the scientific evidence. And certainly, folks who express concern about the impact of addressing climate change on business, that's a legitimate concern, but that is not a reason to deny the science behind climate change and global warming. And the difference there, climate change, well, we'll talk about it actually. So here are the notes. This should be familiar to you. Frankly, one of the confusions comes from the fact that scientists are actually well aware that nature has been a factor in climate change in the past, and we don't have time to get into all of the details, but it is in fact understood that without human influence, climate and temperature has changed over time. First thing that we're going to take a look at briefly are these changes in orbital relationships, changes in the Earth's relationship to the sun. And you don't have to memorize all these details, but basically, over time, the shape of the orbit has changed, the direction of tilt has changed, and the amount of tilt has changed. And originally, we said it was tilted 23.5 degrees, pointing to the north. And in fact, all of these factors change over a period of time. So this guy's face might seem a little odd for me to show you a painting of some random old guy. But in fact, he is credited with discovering these changes in orbital relationships. Newton Milankovitch calculated what we now refer to as the Milankovitch cycles, which are these factors right here. And he actually did that, fascinatingly, with a pencil and paper while he was in jail. That's a whole other story. You can look him up. But he made all of these very detailed calculations without the use of a computer. And then subsequently, later, it was all confirmed through use of supercomputers. So briefly, what are we saying? Again, that the shape of the orbit changes over a long period of time. Notice I've given you the cycles here over 100,000 years. So it goes from rounder to flatter to rounder. And all I want you to know is this affects how much energy we get from the sun over time. Notice in this case, you're a little bit closer to the sun, so that does give you a little bit more energy. If you were over here with a flatter orbit, and you were at the farthest point away, you would get less energy. So all of these things seem subtle, but when they conspire together over time, they're significant. The direction of tilt, they talk about it being Earth's wobble. Over 26,000 years, goes from north, which it is now, all the way around east, south, west, and back to north. And then the amount of tilt. Right now it's 23.5 degrees, and it is, but it does fluctuate over time between 24 and 22. If you put all of these together, naturally speaking, we should actually be seeing a very slight cooling, nothing like the patterns we're seeing. So the message here as we study these natural factors is each time that we look at them, they have been studied and they are past factors, but they are not influencing the current warming. We cannot look at this and have it explain why we are currently warming. Now, a few other things that I'm going to briefly mention. Solar variability, the output of the sun we know changes slightly over time. We don't have time to get into the science, but it has been studied now, and the sun warming up is not the current cause of Earth warming up. Plate tectonics, the movement of large land masses, can affect climate. It is not what is affecting climate now. And then finally, volcanic activity. It is documented that large amounts of volcanic ash can explode into the atmosphere and block the sun, and cool Earth down slightly. So we know in the past, and we have seen brief periods, but nothing about volcanoes can explain the current warming. And I will let you read about this nuclear winter hypothesis. So again, the key here is that, yes, climate changes naturally. You hear people talk all the time about, oh, global warming, it's just Earth's natural cycles. Well, that's only half true, and because it's only half true, it's not true. None of these factors can be currently pointed to as the reason for our current warming. That's the big deal. So then, in fact, what is? Well, what are the anthropogenic factors? What are the human-caused factors? Greenhouse gases, the fancy term is radiatively active gases, and the very first one we're going to look at is carbon dioxide. That's the big player, and humans are the primary source of it. So this was taken early May 2020 from, it's a graph from a sampling site very high on a volcano, Mauna Loa in Hawaii, and the sampling site is really far from sources of human CO2. So it is a good sampling of the atmosphere. And what do we see? They've been sampling there since 1960. They've been doing it very carefully. And every year it goes up and down, up and down. And it does that in response to the seasons, especially in the northern hemisphere. Now, we don't have a lot of time to get into it, but this zigzag is completely natural. It goes up, frankly, it peaks around this time of year that I'm recording this, April and May, when the long northern hemisphere winter has left lots of CO2 in the atmosphere. And then as an explosion of spring and summer growth of trees and plants and grass and all of that stuff begins to suck in CO2, because that's what plants do, they suck it in, then there is a dip, so that it goes down, down, down through the summer, and it reaches its lowest at some point around October. So the zig and the zag up and down is natural, but since 1960, what do you see? It zigs and zags, but it consistently goes up and up and up. Nothing we know about studying CO2 can explain this except for human sources of CO2. Here is another graph over an incredibly long period of time. We can go back 800,000 years and look at CO2 in the atmosphere, and we'll talk about why that is. And we know it has gone up and down and up and down and up and down and up and down. Excuse me. What we then know when we look at the most recent bit of this graph, here's the Industrial Revolution, when we got really good at burning fossil fuels. And then what happened? Within the span of a few hundred years, compared to 800,000 years, it completely skyrocketed. And this value here says 402. Now, scientists really never thought it was going to go over 400, and it is at about 417 parts per million. That is a fraction of a percent, but here's the deal: is I really didn't define a greenhouse gas. It is a gas that is incredibly efficient at absorbing long-wave energy. Essentially, they are heat-trapping gases. So small amounts have an incredible influence. So what are we doing? Well, since we got really good at burning coal, oil, and natural gas by digging it out of the ground and pumping it out of the ground and burning it, the CO2 concentration in the atmosphere has absolutely skyrocketed over the same period of time that we have been warming. Now, is that just a random coincidence? Likely not. So a few facts about CO2. Levels are higher than at any time in 800,000 years. Levels are increasing faster than at any time in 800,000 years. Both those are two different things and very significant. It comes primarily from the burning of fossil fuels, coal, oil, and natural gas. Now, certainly the 2020 pandemic and the subsequent downturn in the economy will be something that climate scientists study as they look at the drop in CO2 from human sources and what influence that will or won't have. That'll be quite interesting. Let me also say that rainforests play a key. When there is logging in rainforests, there's two things that happen. One is you lose trees, and anything that's green and grows is a CO2 consumer. It sucks CO2 out of the atmosphere. It basically cleans it. It scrubs it. So if you cut rainforest down, you lose that scrubbing ability. And then tropical logging is always followed by burning. And burning of the leftover debris, the leaves, the twigs. They certainly don't burn the trees. The trees are valuable. They make things from the trees. They sell the trees, but they burn all of the leftover slash. And in that smoke, there is also CO2. So this is really fundamentally the story of carbon dioxide. Let me say, when you drop, there is a question sometimes about whether the carbon dioxide that we have measured in the atmosphere is actually coming from human sources of carbon dioxide. And what we have here in the pink is atmospheric carbon dioxide. Okay, this is right about here is when we start measuring it on top of the volcano in Hawaii, but we have other means of measuring it, and I'll briefly mention that. So right about this shows atmospheric CO2, so 280 parts per million. Then from 1750, it just rises. And then what do we have over here? CO2 emissions in billions of tons. So this is CO2 burned or CO2 from the source of fossil fuels. So in 1750, well, it's basically zero. Look at the number over here. And then as we roll along, starts to creep up in the mid 1800s as we get better and better at burning fossil fuels. And then what does it do? Well, as we move into the 20th century, we get incredibly good at burning fossil fuels. Right here is the Great Depression with a huge dip in the burning of fossil fuels. It looks like there's a slight dip right here after this dip. So that may suggest what we will see in 2020. But the point is, human sources of CO2 just skyrocket at the same time that CO2 in the atmosphere goes up. So these two graphs, being as parallel as they are excellent proof of a correlation. Let me also say in your notes that it mentions other greenhouse gases. Briefly, methane is actually a stronger greenhouse gas, and it is increasing faster. It is increasing at 1% per year. So there is an incredibly tiny amount of methane, but the thing about methane is that it is deeply influential, and it comes from a lot of situations. Literally from the inside of livestock, cattle and sheep, and I will let you read more about that, but you can imagine how gases escape from inside cattle and sheep. People laugh at this research, and it has been examined by many different scientists and found to be influential. Also, agricultural fields, rice fields, the burning of vegetation. Methane comes from a lot of different sources, and we actually discussed it in this last exam 4 section of notes when we talked about pollution. So you can go look up methane. And methane is one that we're continuing to be concerned about. We think that sources of methane may continue to increase even faster. And also on the list, we're not going to talk about them, nitrous oxide and chlorofluorocarbons, CFCs. So this graph shows over 600,000 years. It shows carbon dioxide going up and down. It shows methane going up and down. And these ups and downs are in relation to the Milankovitch cycles. They're in relation to the changes in Earth-Sun relationships. And again, there isn't enough time to go into all of that detail, but American River College does teach a class in climate change where you'd learn about this. And then we have ways of looking at temperature in the past, and temperature has gone up and down in relation to carbon dioxide and methane, but that is not what we are currently seeing. We are not seeing past natural influencers. We're basically seeing human sources of greenhouse gases. This graphic illustrates just briefly what it is, how it is that we know about atmospheric concentrations of gases from a long time ago. Is that some genius, and I say that truthfully, realized that if you dug into glaciers, what do glaciers do? Glaciers pack snow on top of snow on top of snow, and glaciers trap little bubbles of ancient air. And if you do it right, and if you core down and drill down into there and pull out the ice, you can sample these little tiny ancient bubbles of air. And again, this has been looked at by hundreds and hundreds of professional experts, and they have determined that it's rock solid science. So we do have a record of carbon dioxide going back 800,000 years. We do have a record of methane going back 800,000 years, because that's how old those glaciers are when we dig deep down into them. So then the question is, how has this impacted temperature? What are the current temperature trends? And I'm going to let you read this. I'm going to highlight this, but I'm going to show you a few graphs. So the short answer is, here is a graph that shows global temperature. So it's taken thousands of readings from sites all over the world over what's called a thermometer record. So starting about 1880, basically thermometers were A, high quality enough, and B, distributed far enough around the world, and C, in places where people were writing down and noting the temperature. So those three things: thermometers were good enough, they were distributed around the world far and wide enough, and people were recording the data. And so what does this graph do? This graph takes basically all of the temperatures since 1880 into the 21st century, and it averages them. And then it sets, on this graph, it sets the average to 0, and it graphs every single year. So each little blue dot is every single year as to whether it fell below the average for the entire record of data or above the average for the entire record of data. So even though these numbers here simply show 0 and slight positive numbers, slight negative numbers, they're showing, relatively speaking, the change in global average temperature. So if we go back to the late 1800s, what do we see? It was about 0.2 Celsius below. In this case, in early 1900s, it's about 0.4 Celsius below. And then what do we see? As we move along, the red line is simply a smoothing of the blue line. It's an average. And so what do we see is temperature increases, 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 increases. So at its highest, it's about 0.6 Celsius above the average. At its lowest, it was about 0.4 Celsius below the average. So what does that tell us? Well, the take-home message here that I want you to note is, over the last approximately 140 years, global temperature has increased, actually now just over 1 Celsius degree. That's almost 2 Fahrenheit degrees. That doesn't seem like much. That actually seems like a small amount. It is, because it's a change in the global average, that is a big, big deal. So this graph demonstrates that. Here is a graph from NASA. That's what where the data comes from. That essentially shows the same thing, but it shows it in a bar graph form. So this is pretty much the same graph, and this is showing it, by the way, in Fahrenheit. So here's the 0 line. We can see that before 1930, everything fell essentially below 0, and then we had a little bit of fluctuation. And what do we see starting in the 70s is an incredible, significant increase in temperature. By the way, one of the reasons we think it was lower here is we weren't regulating air quality. So the bad air actually blocked some of the excess um, solar energy. So we think it was unnaturally low here because there was such bad air. Well, what did you learn happened right about here? The Clean Air Act. So we cleaned the air, and that allowed us to see the impact that we were having on global temperature. This is a graph of the 10 warmest years on record. And interestingly, if you take a look at the top 6, they are the 6th warmest years on record. So if we go back basically 140 years and we look for the warmest years, they are in this order, starting with 6, 2014, then 2018, 17, 15. Last year was essentially tied with 2016 for the 2 warmest years on record. And again, you can see the anomaly. This is right about 1 Celsius degree. So the question then is, again, and I've already talked about this, this is pretty clear. Few people are arguing anymore that we are going through a warming period. But people still continue to argue, oh, it's just nature. It's part of Earth's natural cycles. So the basic question is the warming anthropogenic? How do we know? What can we point to? And I'm going to summarize this here, essentially things I've already said, but I'm going to try to summarize it as clearly as I can. So first of all, any discussion of whether the warming is anthropogenic starts out with the fact that there is no evidence that any natural factors are causing the current warming. So again, does climate change naturally? Yes, we are aware of this. It's been studied, but there is zero evidence that any natural factor is causing the current warming. And then what do you say? Well, observed global temperature increases correlate. They line up closely with observed global CO2 increases, which correlate closely with observed human sources of CO2. So these 3 things collectively, and I use the word correlate, that's more of an official statistical term, but they line up very nicely with each other. So we're seeing CO2 increase in the atmosphere. I already showed you a graph that tracks that very closely to human sources of CO2 by burning fossil fuels, and then over that exact same time frame, we are seeing temperature increase. So is all of this a coincidence? It is absolutely not a coincidence. So if you are talking with someone who insists that it's not humans, this is essentially the answer, and then you drop the mic and you step away from the argument. And again, let me reiterate that among the thousands of professional expert scientists, this is not an argument, this is not a controversy, this is what is happening. There are occasional relatively subtle disagreements in some of the science, but nothing that contradicts what we are seeing here. So then there's a question of, well, okay, so who cares? Some people say, oh, I like warmer weather. And in fact, this has potential and is already being seen to impact the globe in a number of different significant ways. I am, we'll do a part 2 here. We'll stop right here and then choose to do a part 2. So stay tuned.